So now let's talk about our final topic for the week, which is inverse functions. So remember that functions are relations, so let's go back to relations for a minute. For a relation R from a set A to a set B, the inverse relation, and the way we denote it is R inverse, is from B to A, is defined as R inverse is the collection of BA where AB is an R. So you're essentially flipping your ordered pairs. So let's look at an example. If A is going to be the set A, B, C, D, B is going to be the set 1, 2, 3, and R is going to be the relation A goes to 1, A goes to 3, C goes to 2, C goes to 3, D goes to 1. So remember, R is just a relation, it's not a function. Then what is R inverse going to be? Well, to get R inverse, all we have to do is flip our pairs. 1A, 3A, 2C, 3C, and 1D. Okay, so we know what an inverse relation is. And remember, our function is a relation, so we want to ask the question, we'll say question, when is the inverse of a function a function? So you can think in terms of pictures, right, of a function from, let's say, from A to B. Well, it's essentially that you're flipping the arrows. Well, if I flip it, this won't be a function because this element here in B doesn't go anywhere. So your function needs to be on 2, and it also needs to be 1 to 1 as well. So those two conditions need to happen. So that's this following theorem, theorem 10.15, says if I have a f from A to B, that's a function, then the inverse relation f inverse is a function from B to A if and only if f is bijective. So in order for the inverse to be a function, f needs to be bijective. And this theorem does say a little bit more. It says if f is bijective, then f inverse is also bijective. So in this case, we would call f inverse the inverse of f, or we just call it the inverse function. So let's look now at this inverse function. So remember, f goes from a to b, and now f inverse, if f is bijective, it's going to go from b to a. And so let's look at both compositions here. So let's look at f inverse composed f. So this is going to be a function from a to a. If I flip it and look at f composed f inverse, this is a function from b to b. These are both defined. And remember how the inverse works. We're gonna, let's suppose a is an a, and suppose f of a equals b, then this pair AB would be an f, which means if I flip it, BA would be an f inverse. So we could write f inverse of B is equal to A. So now, what I'm going to state is that f inverse composed f is the identity on A, and f composed f inverse is the identity on B. Now I'm not going to prove these two equalities here, but because you're going to have it in one of your homework assignments. All right, so finally I want to mention this theorem 10.16, which says essentially the inverse function is the unique function that satisfies these two equations here. So it says if f goes from a to b and g goes from b to a are two functions such that g composed f is the identity on A and f composed g is the identity on B, then I know that these two functions f and g are bijective, and really more importantly, I know that g is f inverse. So the inverse function is the unique function that when you take these compositions, you get the identity.